Uh, Hello everyone. This is Yusuke speaking. This is the fourth week of my part. Today, we will learn link analysis techniques to find the important nodes in large-scale graphs. Today's topic is different from the collaborative filterings, which I already explained in previous weeks, but the link analysis is quite important today. Let's start. Today we focus on the graph data. What is a graph? As this figure shows, a graph is a data structure consisting of a set of nodes and edges. Each edge on graphs represents the relation between the two nodes. We often call edges links. Also, we often call this kind of data this kind of data network data. But mathematically, this kind of data is often called graph. We often observe various kinds of graph data in our daily life. The most popular graph data is social network data. Another popular example of graph is paper citation networks. The web is also one of the most popular graph data. One unfamiliar example is neural networks, economic networks, and so on. When we have graph data, we often want to find which nodes are important in graphs. For example, in social networks, we want to know who is the most influential person. In the case of the paper citation networks, we want to know the best paper, which is the best paper in this graph. In the case of the web, we want to find popular web pages. Here, the point is how we can compute the importance of nodes in graphs. For this question, the link analysis can help us. So today we will learn two techniques to compute the importance of nodes in graphs. Firstly, we will learn the PageRank algorithms, and then we will learn the topic-sensitive PageRank. So let's start with the PageRank. As you may know, the PageRank is one of the most famous algorithms in the last 30 years. The PageRank is introduced by Google to measure the importance of web pages. Currently, Google doesn't depend on only PageRank so much, but PageRank is still important. This is because the concept of the PageRank can be applied to various kinds of graph data. Let's suppose we have graph data where the nodes represent web pages and edges represent hyperlinks between the web pages on this slide. Okay? Then the PageRank evaluates the importance of each web pages by considering the graph structure like this. How can we evaluate the importance of the web pages on this graph? A simple method is majority voting. That is, if a lot of web pages links are web pages, we think that such web pages can be important. So let's think about this method on this graph. Here we find that the page B has 3 in-links. Page C has 2 in-links, and page D has 2 in-links from A and B. Okay. Based on this simple method, majority voting, we think that page B is the most important on this graph because the number of in-links for page B is the largest. Okay, the number of in links for page B is 3 on this graph. So this majority voting approach is often used in our daily life, and so the majority voting approach seems good to evaluate the web pages. However, is this approach really good? If we use this majority voting approach to evaluate the web page's importance, we will have serious problems on the real web. I showed several problems here. At first, there exists a malicious website on the real web. Such malicious websites can intentionally increase their importance scores. Let's assume that we are the web page owner of page C here. Okay. On this figure, if we apply the simple majority voting method to evaluate the web page importance, page C importance is 2. Let's assume that we are malicious and we want to intentionally increase the importance of web page C. How to do it? That is very easy. If we create a lot of web pages and we make the web pages, such web pages link to page C, and then the page C can get a high score. So this example shows that the simple majority voting method does not work well to evaluate the importance of web pages. This is because that the simple method does not consider whether important web pages or not non-important web pages link a web page. For example, let's think about this graph again. On this graph, page C has 2 in links and page D has 2 in links. The number of in links on page C and page D is the same, 2. But the sources of the in links are different from page C and page D. Then, which is more important, page C or page D? The PageRank algorithms can handle this solution, this situation. The basic idea or assumption of the PageRank is like this. If a lot of important pages links are web pages, then such web page can be important. So let's see this graph show again. Now let's assume we know that page B is more important page E. Okay, here page C has 2 in links, page D has 2 in links, but page D is linked by more important page B than page E. Okay, and so we consider that page D is more important than page C. This is the basic concept of PageRank. Okay. We can have another interpretation of the PageRank concept like this. Now, when browsing the web pages, we assume that they randomly select a link on the page for the next browsing target. Okay. Also, we assume that the people are likely to move to a web pages from by using the links to more important web pages. As a result, people are more likely to stay on more important web pages. The question is how can we calculate the likelihood to stay on each web pages? So let's think that using this toy example. Here we assume that this random surfer is now on page A. then we think that this surfer's probability on staying on page A is now 1. Okay. Here he randomly selects one of the links on each web pages to decide which pages he will visit next. The question here is that which page has the biggest chance of this surfer to stay after he moves repeatedly. Let's calculate such probabilities. At first, he is now on page A. As I already said, he randomly selects a link on page A to move next from the page A. Okay, page A has 3 outlinks. That means he selects one of these 3 links with 1/3 probability. Okay. So I have a question for you. How large is the probability that he will stay on page B after his first transition? We can calculate such a probability like this. Before his first transition, the probability that he stayed on page A is 1. If he stays on page A, the probability that he selects a link from A to D is 1/3. The probability that he will stay on page B after his first transition is 1 by 1/3. Okay. The next question is how likely he is to stay on page B after his second transition. I remind you that this user's probability of staying on each node after his first transition is like this: 1/3, 1/3, 1/3. Okay. As I already said, this users randomly select one of the links to move next on each web pages. And so transition probabilities on each web page are like this. For example, page B has 2 outlinks. If this user stays on page B, he will move from page B to page A with 1/2 probability. I show the transition probabilities and the user's probabilities to stay on each web pages after the first transition on this graph. So on this slide, so each probability like this. Now we are ready to calculate the user's probability to stay on each web page after the second transition, not first transition. Okay, let's calculate the probability of the user's stay on page A after the second transition. Okay, there are 2 possibilities. The user stayed on the page A after the second transition. Okay, one case is that the user moves from A to B in the first transition, and he moves from the B to A in the second transition. Okay, and as we already calculated, the user's probability on staying on page B after the first transition is 1/3. That's why if the user moves from A to B in the first transition and and he moves from the B to A in the second transition, the probability is 1/3 times 1/2. Okay. The second case is that the users moved from A to C in the first transition, and then he moves from the page C to A in the second transition. As we already calculated, the user's probability of staying on page C after the first transition is 1/3. Okay, that's why if the user moves from page A to C in the first transition and he moves from the page C to A is the second transition, the probability is to stay page A after the second transition is 1/3 times 1. From these two case observations, we can find the user's probability stay on page A after the second transition is totally 1/2 by using this mathematical procedure. Okay. When we calculate the other pages probability with the same procedures, we can find the probability of the user to stay on each web pages after the second transition like this. Okay. What happens when we calculate the probability to stay on each node after the fifth transition? We can calculate such probabilities by repeating the probability calculations. This table shows the change of the probabilities in the iteration of analysis. Okay. Here we have a question. When transition repeats infinitely, what happens? What will happen? The answer is the probability will be converged. The probability will be stable after the infinite repetition. In the PageRank algorithms, this converged probability is regarded as the likelihood of people to visit each web pages. And also, we finally regard this converged probability as the importance of each web pages on the PageRank algorithms. This is about the basic idea of the PageRank. So we can handle these PageRank computations by using mathematics, especially linear algebra. Let's see the mathematical procedures to calculate the PageRank scores. At first, we represent the initial probabilities of users to stay on each node before starting transition by using the vector R0. Okay? And also we represent the transition probabilities from node to node by using the matrix M like this. Then we calculate the probabilities to stay on each node after the first transition by multiplying the transition matrix M with initial state probability R0. Like this. Okay? How can we calculate the probabilities to stay on each node after the second transition? That's very easy if we do matrix calculations. The probability R2 is calculated by the multiplying transition matrix M with R1 vectors. Okay, which we obtain after the first transition. The probability R1 is calculated by the matrix M times vector R0. So then, the probability vectors R2 can be calculated by the matrix M times vector R0. Okay, like this. The following this mathematical operation, we can obtain the state probability Rn after the n times transition by calculating the nth power matrix, nth power of matrix M times R0 vectors. Okay, if n is large enough, we think that the probability Rn represent the likelihood of people visiting each web pages. This is the mathematical procedure on the page rank calculation. However, we have to modify these mathematical procedures for the practical application of the page rank. The simple page rank, which I already explained in previous slide, has several serious problems. Several types of the link structure violate the page rank assumption. So here is the malicious one of the links structure which violate the page rank assumption. One is a dead end structure. Dead end link structure is one example. Here, a node C has dead ends on this graph because if users move from A to C or from D to C, he cannot go out from page C. This is a dead end link. Okay, if we apply a simple page rank algorithms to this graph, the final page rank values for all nodes become 0 like this. This is from the dead end link structure. The spider trap structure is another example which violates the page rank assumption. On this graph, node C has an outlink from C to A, and also the C has self-links to itself. This self-link is not good when using the simple page rank. If we applied a simple page rank algorithm to this graph, page C has collect the scores from other pages, as this figure table shows, like this. Okay. How can we solve these problems? This is about the idea of complete PageRank algorithms to solve such problems. Okay, in the complete PageRank algorithms, we have two assumptions. The first assumption is the same as the simple PageRank algorithm. Okay, when browsing the web pages, we assume that they randomly select the links on it for the next transition. Okay, this is the same as a simple PageRank algorithm. In addition, as a second assumption, we assume that sometimes people directly visit the web pages without using the hyperlinks. For example, let's imagine this user is now on page B. Page B has hyperlinks from page B to A and from B to D, but this users does not use these. Sometimes this user does not use these hyperlinks, and he moves from B to C by inputting the page C URL into his browser. This is the second assumption case. So based on these two assumptions, we modify the simple page rank calculation mathematical procedures, this formula shows. At first, we initialize the vector R0, matrix M, and vector D. vector R0 is the probability of the user to stay on each node before starting transition. Okay, matrix M is here the transition matrix, and the vector D is a random surfer vector. Later I will explain the meaning of this random surf vector. Once we initialize these vectors and matrix, we update vector Rn by using this formula starting with n equals 0. So this formula consists two parts. The first part corresponds to the case where people use the hyperlinks to visit other pages. Okay. So this part from the simple PageRank algorithms, which I already explained in previous slides. Okay. The second part of this formula corresponds to the case where people directly visit the web pages without using the hyperlinks. Here, the vector D is called a random surf vector. This vector represents the probability of the people visiting the web pages without using the hyperlinks directly. Typically, we set uniform distribution of the probabilities to this random surf vectors, like this. On this graph, a random surf vector is 1/4, 1/4, 1/4, 1/4. Okay. So the complete PageRank algorithm considers these two factors. So by the way, what is this alpha? This alpha means the probability to decide which of two factors people use. The case of using the hyperlinks or the case of direct access to web pages. Okay? Empirically, this alpha is often set in the range from the 0.8 to 0.9. Okay, so we compute the PageRank values of web pages by using this formula. If Rn is converges, the complete PageRank algorithm will stop. Then we use the converged Rn vector as the final PageRank values. Let's compare with the simple PageRank algorithms and the complete PageRank algorithms on this spider trap example. If we apply the simple PageRank algorithms to this graph, page C's PageRank score will be 1, and other pages will have 0 values. But if we use the complete PageRank algorithms for this graph, we can obtain the score of all pages like this. The result comes from the complete PageRank algorithms. Okay. So in today's lecture, we learned how to use the PageRank to measure the web page's importance. But the PageRank algorithms can be applied to the various kind of the graph data. For example, if we apply the PageRank algorithms to social networks, we can find influential people. If we apply the PageRank to paper citation networks, we can find a good papers to cite. Okay. If we apply the PageRank to the web, we can find the popular web pages. The PageRank is very powerful very powerful and very useful to evaluate the centrality of nodes in graph data. So that's why the page rank is often used and very important. Okay, that is all about the page rank algorithms. Okay, so next I will talk about the topic sensitive page rank, which is an improved versions of page ranks. The normal page rank is very powerful, but the normal page rank algorithms ignores what kind of topics each web page on graph is related. I show you one example. Here, this graph shows some web pages and their link structure on the web. On this graph, the red color nodes about the medicine. On the other hand, the blue color web pages about the cosmetics. If we apply the normal page ranks, which we already learned, to this graph, we can obtain the importance scores of web pages as right hand side. This information shows. Okay. As I already explained, the normal page rank algorithms measures the importance of web pages without considering topics. Of course, the normal page rank score is very useful if we want to know the global importance of web pages. But if we want to know the importance web pages from the viewpoint of the medicine, what should we do? So let's think about one example. Is page C here is page C important from the viewpoint of medicine? As you can see, 4 web pages link to the page C from A, E, F, and D. But 3 of 4 web pages, that is the D, E, F, are about the cosmetics, not medicine. Only page A is about medicine. On the other hand, page A is linked by the many web pages about, not many, page A is linked to 2 web pages about medicine. What should we do? One assumption is that if people often move to web pages from the important web pages about the topics, such a web page should be important. This is the one assumption, and the topic sensitive page rank is based on this assumption. So let's compare with the assumption of the normal page rank algorithms and the topic sensitive page rank algorithms. The normal page rank has 2 assumptions. We assume people follow the hyperlinks on web pages to visit other web pages. Also, we assume that the people sometimes randomly visit the web pages without using hyperlinks. Okay, these are assumptions about the normal page rank algorithms. On the other hand, we have 2 modified assumptions on topic-sensitive page ranks. At first, we assume the people follow the hyperlinks on web pages to visit other web pages. This assumption is also used by the normal page rank too. The next assumption is modified from the normal page rank assumptions. We assume that people sometimes randomly visit only web pages about the target topic without using hyperlinks on the topic sensitive page ranks. Let's see how to reflect these assumptions on normal page rank mathematical procedures. So we modify the normal PageRank formula slightly, like this. This formula on this slide comes from the normal PageRank. The first factor is related to a transition matrix. This factor is the same as the factor of the original PageRank. But the second factor is modified on the topic-sensitive PageRank. When using the normal PageRank, we set the uniform distribution probability on to this random subvector. On the other hand, when using the topic-sensitive PageRank, we set uniform distribution probability to only web pages about the target topic on a random subvector, like this. In this example graph, only red colors web pages about the medicine. So now that we want to find the important web pages about the medicine, so then we set the uniform distribution probability to only red colored web pages, like this. The difference between the normal PageRank and the topic-sensitive PageRank is this, okay? So, but the modification effect is very large, is larger than we expected, okay? These are results when we applied the normal PageRank and the topic-sensitive PageRank to this graph. When using the normal PageRank, as you can see, the normal PageRanks orders the measure the web page without considering the topic. On the other hand, when using the topic-sensitive PageRank, web pages about the target topic get higher scores than the non-target topic web pages. Okay. Also, even if a page is not about the target topic, for example, page D, if important pages links the page, important pages about medicine link this page, the topic sets the PageRank gives a high score to page. So this is about the topic-sensitive PageRank. Okay. So when do we use the topic-sensitive PageRank algorithms? There are several use cases. One use case is when we want to find important nodes on graph for target topics. Another use case is when we want to find important or favorable nodes for individual users. This second use case is called the personalized PageRank. If you know the nodes of a user to frequently visit, you set the random sub values to only such nodes. So then you can calculate the personalized PageRank scores, which is optimized for the target users. That's all about today's talk contents. Okay. Okay. To learn PageRank algorithms practically, I have prepared the programming work materials. I have already uploaded the several materials on this URL. Please visit this URL. Then click this link, the fourth link, to learn the link analysis. Then your browser open the programming materials on the Google Collaboratory website. At the last programming work, all programming codes are ready to learn. All you have to do is to learn the ready code to see how the PageRank algorithms works. So enjoy them. That's all about today's lecture. See you. Bye bye.